Welcome. I'm Elizabeth Stage, and I'm the director of the Lawrence Hall Science. And I think it's wonderful to have the Reflecting on Practice group here. I think it's wonderful to have the Communicating Ocean Science in Formal Environments Network here. And I think it's wonderful to have so many Lawrence Hall Science staff here. And I think it's most wonderful to have Jeremy Roschelle here. And I'm not going to take up barely any time except for to tell you that we're all extraordinarily lucky that Lynn, Catherine, et al. Have garnered Jeremy to talk with us, because he's really, really interesting and he's also fun. So thank you, everybody, and let's give a big round of applause to Jeremy Roschelle.
Well, thanks. That's wonderful. So I'm going to talk today some about learning technologies, and I'm just really excited about the conversations I heard this morning and how engaged everyone is about thinking about how to help young learners learn really important science, much of it ocean science, I understand, and I have to admit I love the ocean, but I'm not an ocean scientist, and I'll actually talk some about math today because that's what I've done a lot of, but also try to bridge into some science for you as well. One thing I want to check is if I stand over here and talk, can you still hear me, or might you have to stand right there? Can you hear me up in that? Thanks, because I don't like to have to stand just in one place. I just want to start very briefly telling you a little bit about SRI, just so you know where I come from. SRI is a nonprofit research institution. It's been going for 65, 70 years. It has a lot of people. We're proud of the many things we've invented over time. One of them was the mouse. Many things that you use every day. It's a very fun place to work, and I mention it in part because we do a lot of work in the area of education, both informal and formal education, and are always on the lookout for new partnerships and new opportunities to do the kind of things that you're doing. So part of my reason for being here is to help you, make the relationship to SRI as a potential partner. And here's where I work specifically. I co-direct a center called the Center for Technology and Learning. We have about 65 or 70 people on our staff. We do research for the National Science Foundation and the U.S. Department of Education, doing studies on mostly how to improve science and math learning, mostly. Also, mostly sort of centered on middle school, but moving outwards. We also do work for private foundations. We're the evaluator on the Gates Next Generation Learning Challenges, for instance. We do some direct work for different states in the country and also different countries. And we also do a lot of consulting with companies that are active in the educational technology market. I've personally done a lot with Texas Instruments that makes all the graphing calculators, because they're very interested in how to improve those devices for kids' use. And our group is very diverse. That's what our group does is along the bottom here. We do work in evaluating things, figuring out how things work. A lot of work on how to improve learning of science and math content. We do a lot of work with teachers. That's the next one over. In the area of assessment, we build new tests, new ways to measure. Particularly, we're always interested in how do we get at the deep learning. There's lots of people who can make the next multiple choice quiz, but how do we get at the deep learning? That's a big emphasis. And we also do work in informal learning. We have a practice that focuses on learning in museums, computer clubhouses, and the like. I knew many of you were there, and we design new things. And I wanted to briefly just say something about myself. You're reading some things that throughout the day that I know I've written over time, and I think there's some different stages in the work I've done. Some of the things you're reading go back to when I was a graduate student at Berkeley, when I was very focused on prior knowledge and misconceptions, and some of it goes back to work with Gene Bamberger, who was my original inspiration to enter this field. Delighted to have Gene in the audience today. And so, the work on prior knowledge I have a lot of deep interest in, and also it's not exactly what I've been doing most recently, and I'll show you some of what I've been doing more recently. Then I did a stint at a place I like to call the University of Massachusetts San Francisco campus. I was the only person on that campus. I worked on a wonderful research project from home in San Francisco with Jim Caput at UMass. And I moved then from working on science to working on mathematics. And ever since, I've done more work in the area of math than in science, and particularly around technology. And since 1997, I've been at SRI, And a big focus for me has been scaling up. How do we take the stuff we know and make a bigger impact with it? How do we get it to more people? How do we keep it robust as we're doing that? Okay, so here's what I thought I would share with you today. We advertise this as one of the things I like to do is I like to reflect on, well, we have all this learning research, and it's in tons of journals and lots of articles, and everyone's got their slightly different views on exactly how to say each thing perfectly. But when you step back from that and look down from 35,000 feet, what are really the big things that we're learning? And I want to share with you some of what I think some of those big things are, because I think they're things you should work with and you are working with every day in your work. And then I want to show you some examples that use those principles. And we'll see how many we get through. I'm going to share with you the largest piece of work I've done, the scaling up SimCalc work. Maybe talk about a little collaboration and formative assessment with the group Scribbles work, and how we're working with teachers to deepen their engagement with student thinking in the Dynabook work. So that's my plan for today, just to start out with some big principles and then talk about 3 specific examples of work. Why do we need principles? Well, talk to your average parent out there, and there's a million reasons why you might want to use technology. And you go to your average PTA meeting or talk to another parent around the swimming pool or at the tennis court, you're going to hear, well, let's turn everything into a game. That'll make learning better. Or technology can personalize learning, so we need to do that. What is personalizing? I don't know. No one actually does know what personalizing is, but it's good. Or kids can learn anytime, any place. Or computers can tutor kids. Or kids need rich media. We have to give them that rich media or they're not going to learn anymore because they're different than they used to be. Use an iPad for anything and kids will learn better. I hear that on the school board. I have parents come up to me or PTA committees, hey, should we buy iPads? Aren't they going to help our kids learn? Don't our kids have to have iPads? Well, I don't know. So without principles, we kind of just are following these waves of fads. And I think we need something deeper to be a good rudder for us in all these different trends. So the work I've done all coalesces. It comes from an area of social science inquiry called the learning sciences. Learning sciences is kind of an amalgam of research from cognitive science and different other areas of social science, all very aimed at real learning with real kids in real situations. It's not very theoretical lab-based work, but it's deeply engaged in practice. So I put How People Learn. That's the signature book. You'll see the subtitle is Bridging Research and Practice. And the reason why I do some of this 35,000 foot stuff is people don't have time to read all these journals. They're dense. They're hard to read. And even when you're finished reading something, you're not quite sure what you just heard. So can we kind of step back from that to some of the bigger themes that emerge across that literature? Now, here's some things that most learning scientists would agree to, and you probably agree to them too, and so I'm not going to give that much time to them. We all want kids to be highly engaged, right? We believe in that? Highly engaged is good? Yes. Understanding prior knowledge is important. We've been talking about that a lot today. Kids don't just learn tough STEM content. We have to design something for them to learn it. So a lot of our work is about design. How many of you believe that great learning experiences are hardly ever teacher-proof? Got a fair bit. I believe that. It's some of the best learning experience. You need an adult or another person. You need social interaction. You can't design things that teachers are unimportant for. And so these are some things we probably all believe, and I'm not going to go into a lot of detail. And we also value probably some of the same things. Jean would be a person who definitely values the having of wonderful ideas, right? We want kids to have wonderful ideas, don't we? We want them to have hands-on experiences. We want learning to be playful. I would guess that there's many people who have those values around the room. We really want to respect kids as learners and treat them as if they can have responsibility for their learning. We want to nurture curiosity, and one thing I care a lot about is deep understanding of the really important content. How do we get that? So we still on the same page? Doing okay? You guys believe in this stuff? So we believe in a lot of the same things. Now, and finally I wanted to say, this is a slide that came out of some work I did. Elizabeth was there, called the Blue Sky Workshop. It was held by NSF. and it was looking at this phenomenon called the long tail distribution that's happening because we're now all connected through networks and the internet. And so the long tail started, forget about the education stuff here for a second, just think about books and Amazon. It used to be that you can only buy the books that were in the bookstore, and because you had to have physical books there could only be 1,000 or so titles. And so everyone had to choose from the 1,000 or so titles. So we were all having to read common books, and everyone had to read the same ones. But with the internet, the number of titles Amazon can carry now is vast, and the number of specific interests it can serve allows very individualized interests. And what I and others who went to this workshop came to believe is that this is also now true in education. It used to be that if a kid wanted to learn something, there was one place they could go, more or less, school. And what they were going to learn is the things that were most in common to every kid's need. They were going to learn very disciplinary knowledge. But with the advent of informal experiences on the internet, the diversity, we can offer kids very individualized experiences now. And really, things that are very closely related to their growing identity as learners, as young scientists. And the question is not, is one of these better? Is it better for kids to learn everything that's exactly what they're interested in and nothing in the disciplines? Well, no. Is it better for them to do everything through projects? It's kind of in the middle of the spectrum here. I love Lego Robotics League. It's a project that takes most of the fall for kids to do. Kids can learn a lot there. Well, the portrait we're coming to is that this is an ecosystem, and we want to see how it can be connected. How can we connect a great experience a kid might have over here through something I can exhibit at a science museum to something that they're going to be learning over here in school in the core disciplines? Or how can it become the focus of a project? I think this is what we have to provide to our children, is more of an ecosystem in which they can learn. And that's a big challenge for us. We're used to just focusing on our little bit of the puzzle. If you're a school person, all your little bits are over here. Maybe if you're an informal learner person, most of them are over there, or maybe you're doing some projects with kids. How can we make those more connected so kids can leverage the things across that spectrum? Okay, so that's kind of some preliminary remarks on it. Now I want to share some of those 35,000-foot principles briefly with you, and then I want to show you some examples. So what have we learned? And I'm just going to go through 5 things that I think we've learned. The first one's very basic, but we can display things in new ways with technology. And when I mean display, I don't just mean computer displays. I was talking to people about some fabulous use of glass in a polar bear aquarium this morning, where you could see the polar bear swim because you could use plexiglass instead of concrete to hold in that tank. What does it do to create a great display? Well, it's absolutely fundamental to learning. There is no real learning unless you get everyone's attention on the same thing and attention on the right things. So we have to think about displays because they create shared attention, but that's not enough. And you'll see the format I'm going to go through. Just having the display and the possibility of learning is enough. We have to design the task that they're going to do with that display to be a rich task. Something that's really meaningful and is going to get them into the subject matter. And I'm not going to illustrate all of these now because I'm going to give you examples of rich tasks when we do the examples. So I'm just putting these out there as an overall thing. This is one basic connection from technology to learning and to best practices in teaching. How we use displays to create shared attention and to enable kids to engage in a rich task. Here's one I'll spend quite a bit of time with you, is linked dynamic representations. One of the things we can do with technology is we can give students representations that make it easier for them to deeply engage with the meaning of whatever the subject matter is they're dealing with. And so when I worked with Gene many, many years ago, we had dynamic representations of music. And we were using those to get kids, without the cumbersome nature of standard musical notation, to get more deeply into the experience of constructing and appreciating music. And the linking of the notation system to the playing of music was absolutely critical to that experience. Without it, it couldn't be true. And so why we want linked dynamic representations is because meaning comes when things are connected. And these representations help kids do a better job of connection among different aspects of concepts. And we're going to see some of that today. And the best practices really here is teaching for conceptual understanding. That's what we're after with this practice. Okay, another one I'll talk about as we go is a thing technology lets us do is it lets us express and share. Both of those are important. Technology can let kids be more expressive of what they know already and what they're learning. They can draw a picture, they can narrate a video, they can sing a song. Technology can help with that, and technology can help us share what kids are learning. And there was a great conversation this morning about the impact of small group sharing and the explanations that emerge from that on kids learning. And so the best practice, learning, because collaboration is a great tool for learning, it's a great way kids learn. The reason why we want to do this thing is because we want to get kids giving and receiving more explanations. And again, that ties back to conceptual understanding. But I would argue if you just have kids making cool stuff and posting it, and they're not explaining and discussing with each other or arguing with each other, you're not getting the benefit of that technology. Another one that came up this morning was instant feedback. It's something actually technology is great at. And here I'd like to give a little story just for you to sink in, just how important instant feedback is. So imagine you're trying to teach a kid to shoot baskets. Free throws, maybe. And they shoot 3 in a row on Monday. It's Monday morning, right? And then a teacher has to collect the papers and grade them. So on Friday, they find out which one of their baskets went in. Is that kid going to be able to learn to shoot baskets really easily? I mean, you really need to know when you shoot the basket, did it go in? So getting feedback, the appropriate feedback quickly is really important. The learning principles are around formative assessment, that teachers, coaches, mentors are more effective when they know what students know and don't know, rather than teaching a blank slate with no idea where that kid is. And so formative assessment is the key area. And what we really want out of that feedback is we want more adaptive teaching and learning. We want to tighten those cycles of adaptivity. And here's my final thing that I think everyone should know and think about in their work. And we'll make these slides available, I'm sure, to everyone. So if you haven't had time to write down a whole table of 25 cells, don't worry about it. We'll get it to you. We'll do some instant expressive sharing, maybe some arguing even. I think a huge boon to what we're able to do in the learning sciences and in practice has come through our ability to record and videotape real kids doing real things with real materials and really see the kinds of both potential in their thinking and the places they struggle. And our ability to capture and annotate in media format how kids think has really been the core of the learning sciences. And it turns out that as far as I can tell, the very best thing to do in teacher professional development is to get teachers or instructors or whoever you're working with to really focus on how kids think. Almost everything good flows from that moment when people get really interested and concerned with kids' ideas and how they think. And you can tie everything around that, but if you don't have that fundamental anchor in the way kids think, it gets very hard to do anything. So I think that's what the learning sciences has really said to teacher professional development. We've got to make kids' cognition the center of everything we do. Okay, those are 5 big principles, and now I'm going to try to illustrate them with some looks at technology that I've been involved in. Anyone got some questions so far? Are we doing okay? Okie doke. So I'm going to start with work I've spent the most time in my career in. It's in math, but as you'll see, it's math that's very relevant to huge parts of science. There's a picture of Jim Caput. He was the professor at the University of Massachusetts. That's the link to the San Francisco campus that I did this work with. And Jim really believed in uses of technology that represented math in new ways. And how did he want to represent math? Well, he wanted to show things as linked and connected. When I talk about links, I'm going to talk primarily about 2 kinds of links. We want to show more graphical representations connected to more linguistic representations. So a graphical representation can be a graph. A linguistic representation might be a story. or it might be algebraic symbols. So graphical, linguistic, but we also want a trajectory for more informal and familiar representations connected to more formal ones. So the story, which I had over here, we want connected to the algebraic symbols. How do those two things relate? Or we might want an animation or a simulation, which might be more familiar, connected to a graph, which would be more formal. So we want to feature those connections. And so here's a picture of SimCalc. I'm going to show it in a second. One thing that's really important about everything we do throughout what I'm talking about here is it isn't just the technology that produces learning. The technology has always been used in conjunction with a curricular workbook that scaffolds and structures what happens in classrooms, and really plans out the activities kids do, and with teacher professional development. So all three of those are always tightly coupled. The concept that I'm going to focus on with you today is the concepts of proportionality and rate of change. And rate of change is just the key, and proportionality, those are the key middle school math concepts. Lots builds on kids making a transition from more additive thinking to more multiplicative thinking. It's a huge transition that happens around that. And I picked some examples across the sciences to show you how important proportional thinking about rates is in every science. So here we have the spring law in physics. It's of course the proportional law that the force is proportional to how far out you stretch that spring. We have an example from chemistry up there. That's an example of rate of reactions. Now, if you just read all the dots on that slide, you're not getting the meaning of that picture. The whole meaning of that graph is about the shape of the curve. And it's showing a reaction that's starting out fast, right, and slowing down until the reaction stops. We need kids to be able to look at curves and interpret them that way. The other one over here is in biology, example of maple leaves, leaves from their trees. And again, unless you see the length and the width as related in a multiplicative way, you're not going to get the meaning of that table. So it's just pervasive proportional reasoning. And we've already kind of done this. This is how the representations connect. So now I'm going to switch to show you a brief demo. And what we're going to do, I promised Lynn that we would be interactive. And I've talked a lot already. So I'm going to involve you as a classroom of students. And I think it's good to get out of the abstraction, and I think also to give you a feeling of the kind of pedagogy that I think ought to go with these technologies. So it's just going to take me a second to open up our example. Not there. Okay. So we're talking about rates, we're talking about proportionality. We start out in a very simple place. We're starting with a graph of position versus time, and a soccer player who's going to run across the soccer field. And so let's start him running. See him running? Hopefully you can see all the way up the top. Is it easy to see? Okay. Okay, so just to get ourselves grounded here for a second, let's look at that graph, and can anyone tell me where is our soccer player going to stop? I've paused him midway, but the graph tells us where and when he's going to stop. What do you think? About 10 seconds, did somebody say? Notice what I'm doing here. This is the pedagogy, folks. I'm not letting the computer run and tell us the answer. I'm stopping and I'm asking you to make a prediction. Asking you to commit, just thinking. Then you can reflect on whether you're thinking largely the right way. Okay, and so people said it's at about 50 meters, right? And so now we've made our prediction. There we go. He stopped at 50 meters. How cool is that? Well, let's do another one. So I'm going to change my graph. This is a neat thing we can do. We don't have to go into equations yet. We can just start with graphs, we can change them, and we can see what's going to be different. So why don't you take just a second, talk to your neighbor, and tell me what we're going to see when we run the animation now. How's it going to be different from what we saw before? They're not getting very far. I heard they're not getting far. Same amount of time, not going as far. Must be slower. Is it working for you as an explanation? Yeah, notice what we're doing. You told me the answer slower. Did I just say, oh great, thank you class, you're all smart? When I asked you to explain, how do you know? Again, the technology doesn't do it. It's the pedagogy plus the technology that helps kids learn. So that's a bit of the pedagogy. Let's have a look. Oh yeah. You're laughing. I hear kids think this is the funniest thing ever. They do. Mostly we've done this with this kind of work with kids in 4th grade up through 8th, 9th, 10th grade. Let's make another one. What's that going to look like? Yeah, and this is very funny, right? It's going to be very funny. Yeah. So we're engaged, we're talking about this, we've learned something, we're grounded in it, and now it's time to do some real math. So let me go to the next thing. This might be a couple days later in the curriculum we do, but now we have 2 guys running, or 2 women actually as it turns out, running on our soccer field. We have 2 graphs, and now we're going to start with our storytelling. So what story could those graphs be telling the story of? What could be going on here? What could be going on? Where are they racing to? See a race? I see some nice explanation going on. People turning to each other and helping them look at the graph. See, it's a race, right? Because they're both going to where? They're going to 50 meters, right? They end up at the same place. Who gets there first? And so who's going faster? Orange, right? So let's have a look. Oh yeah, orange is winning the race. Okay, but that's all qualitative, that's fun. It's time to do some math, guys. So we also have this readout, which goes way too fast, but it's telling you about time and position. And so we're going to make it go slower. And at this point, what we do in a classroom, and you can do a little bit of it too if you have a piece of paper in front of you, is we actually write down some data. Not everything we do is on the computer. A lot of it's paper and pencil, and that's important too. And let's look at Clara together. So those of you who want to play along would write down 0 and 0. At time 0, she hasn't gone anywhere. She's at 0. And let's see where Clara is after 1 second. You guys see she's at 5. She's the blue runner. You can see her blue baton she's holding goes right over the 5. And she's at 5. So at 1, she's at 5. At 2, well, now she's at 10. We're going to write that down. 3, she's at 15. And so now I want you to turn to each other again and tell me what pattern you see in your data. What's the pattern in that data? 1, 5, 2, 10, 3, 15. Go ahead. What do you see as a pattern? Okay, it's quiet again. Can somebody volunteer to tell me the pattern they see? Come over here. See a pattern? Go ahead.
Increments of 5.
Increments of 5, okay. Does anyone have another way to explain it?
5 meters per second.
5 meters, what's 5 meters per second?
Claire's running.
Claire's running 5 meters. Does anyone have another way to explain it? Did anyone write a mathematical expression down? Go ahead.
You said a 1 to 5 ratio?
A 1 to 5 ratio between?
Time and
1 to 5. So these are all great answers, and you can have a fabulous day in math class talking about these different answers. The idea of incrementing by 5 is in fact something many kids say, and there's a danger there of a misconception that kids are only going to see this additively. That they're not going to see that there's a multiplicative relationship between time and distance, and you're only going to see an additive one. So the danger is, if our table were to jump to 6 in time, they wouldn't notice that time isn't going up by 1s anymore. And so we have to work with these, and we can work on different ways to express the math. Let's go with the 1 to 5 ratio right now. Using the 1 to 5 ratio, where do you think Clara will be at 6 seconds? 30. Okay, 30 meters. 6 times 5, 1 to 5 would be 30, and so let's test it. Sure enough. Well, look at that. Math works. It's useful for something. Right? We started with a qualitative experience and a story of a race. And we wanted to know how they were racing and how it was going, so we collected some data. We looked at our data, we found a mathematical pattern, and we tried to formalize that and symbolize it in different ways. And then we used it to make a prediction, and we tested if our prediction was true. Not so different from science, right? Not so different. And the way we're using the tool here is to connect across all the representations. See how we connected those all together? Okay, there's one more example I have to show you. The kids also have a lot of fun with. I hope you'll have some fun with it too. And I like to show it because we're talking about prior knowledge and misconceptions, and this one has a great misconception in it. It's another race. Oh, you guys you still have a kid in your heart. I'm glad you're This is funny. And this is one that it's actually very important to get kids to tell stories about. Because we want to make sure we're all seeing the same thing. A story is a great way to talk about what are we seeing happen here. So hopefully some of you notice that blue just keeps running at the same rate the whole time, but orange does different things. And we could say this is a race, and orange is ahead in the beginning, but drops her water bottle and has to go back to get it because you can't win this race unless you got your water bottle. She's got her water bottle now, she's trying to get back in the race. She sees the other person's right ahead, and she runs as fast as she can, and it ends in a tie. That is exciting. It is. Compared to what goes on in most math classrooms, that's exciting. Now the question is, what's the graph look like? What could the graph look like for that? Some of you doing stuff in your hand, right? With your hands. So let's have a look at what the graph looks like. And what we'd want to do here, that's what the graph looks like, is we want to tell the story of the graph. We want to link our story to the graph. Well, scientists do this all the time. Scientists make graphs, and they tell the story of the graph. I did it a little bit with the chemical reaction. We don't just want to look at the dots in that molecular reaction. We want to know what story it tells us. Well, what story does this tell us? Well, we did the race before, so we know that this is orange winning, right? We know that from what we saw before. And then this line's going down. Well, kids have lots of troubles with what that might mean. They might mean that might be going slower. And what is it in our story? It's going backwards, right? It's going backwards. And so we connect that to the story. Then we start pointing upwards again, over here. And so that's the place in our story where she's gotten her water bottle now. And now she sees blue ahead of her and starts to run again. And then what's going on in that last piece? Yeah, she's going faster, right? So the slow, fast, to try to catch up. And you can see the dots end up together. They win in a tie. Okay, the reason I like to show this one in part is it connects all the features we talked about, the storytelling and the math, but also because there's a really common misconception that this experience can help kids with. And the misconception comes out if you ask, where does that graph show the two runners going the same speed? Where are they going the same speed? So, you know what kids will say? They'll say it's right there. Because the lines cross. Well, it must be the same. That's where they cross. Very common thing that kids will say. And so what we're going to do is a little audience participation now to find out where the graphs really intersect. And so what I'm going to do is I'm going to play the motion. I'm going to start them running. And when we see them going in the same direction, and we see them going the same speed, and you'll see it, I want everyone to clap. Okay? So you got to put down your fingers from your keyboard, Michelle. It'll be okay if you don't get notes on this part, and you have to clap. Okay, when you see them going the same direction and the same speed. All right, we see it. Now look, our graphs paint in colors. You see the orange stops and it's gray. So where are we? Well, where the lines are parallel, right? What does the slope of a line tell you about? tells you about the rate or the speed. So when lines have the same slope, they're representing the same rate or the same speed. This is a huge, big idea and very hard to get kids to, but it carries forward into everything you're going to do in calculus and also in science. And so this is some of the core stuff we work with 7th and 8th graders. Okay, so enough of showing you the pedagogy and a little bit what that's like. Let me just show you some of the results, and then we can talk about other things. So we had the opportunity to do an unusually large-scale field experiment. And I'm not going to go through this in tremendous detail, but in one of the experiments we had 95 different classrooms who were going to do this. They were all spread out through the state of Texas. And what we did is we asked some classrooms, the treatment group, to start teaching in the first year. And when they taught rate and proportionality, which takes 2 to 3 weeks in the standard curriculum, they were going to use this. The other group was going to, for the first year, teach it as usual, and then the second year, they were going to get to teach it the new way. And we randomized them to those two groups, so they didn't know which group they were going to get. So we had 2 groups of teachers randomized. And here we are, we're in the state of Texas. Texas is extraordinarily diverse. The pie up there shows you that almost half the kids in Texas report their ethnicity as Hispanic. That's more and more true in California as well. And here's what our results look like. And I show them in this non-standard way because I think it tells a very interesting story. And as you know by now, I'm into graphs and stories. So let me tell you about this graph. I'm going to make it bigger for you too. So every bar, every vertical bar in this graph represents one classroom and one teacher in that classroom. And the height of the bar is the average of the learning gain while they were teaching, either in the standard way or in our way. They were teaching proportionality. So what we did is we gave the kids post-test and pre-test. We took the post-test score and subtracted away the pre-test score, and that gives you a gain. So that's the average classroom gain. And then we rank ordered classrooms from left to right, the lowest gains to the highest gains. And the green ones were using the SimCalc replacement unit, the gray ones were teaching as usual. So what do you see in that picture? Well, you can see there's a lot of green to the right and a lot of gray to the left, right? And that tells you the main effect of this, that most classroom teachers were got bigger learning gains. Across these 95 very diverse classrooms all throughout Texas with the SimCalc resources. But there's some other interesting stories in here too that I want to point out. We have 2 gray bars near the end here, right? Who are they?
Awesome teacher.
Awesome teacher! Right? Every place has got it. You got your awesome teacher, you don't have to give them anything. You just point them in the direction you go. And so what our job isn't about just helping the awesome teachers be more awesome. We have to help the teachers in here. Right? And you'll see that we had some challenges too. We had some green bars down here who didn't do that well, and so nothing's perfect, right? And that's why I like this picture. It gives you a sense of reality, but also a sense of what the real challenge of scaling up is. So finding a way of doing things that on the average works with everyone. And that's the challenge. Here are the results in a more conventional way. I won't spend much time on that. I do want to spend time on the kind of questions we asked. We asked 2 kinds of questions on the test. Here's a very basic kind of question that you typically find. And you just have 3 numbers, and you plug and chug and you can get the 4th number. This is the question that I showed you with that race situation. And the common misconception, before kids guess at this question, there's 4 possible answers on the multiple choice, and they get 25% correct. They could achieve that by guessing with 4 answers. And afterwards, we see that, well, we didn't help everyone, but we helped a lot of kids. We got up to 55% can get the right answer of when are they going the same speed. I'm going to skip this. Another thing that was exciting about this work is the equity results. So after we got this data, we divided by all kinds of subgroups. And there's lots of charts here. Let's just focus on the bottom. All the charts are the same. The black bars are taller than the gray bars, which means that kids using the technology-enhanced work, on average, we're doing better than the gray bars. And so we compared boys and girls. Is this better for boys only or better for girls? Well, it's better for both. Hispanic and non-Hispanic kids. We had success in both situations. We had teachers rate the kids' achievement level, what they expected of their kids beforehand. The sad thing is you can see teachers are, kids follow the expectations. The kids they think are going to learn the most do learn the most. And the kids they think are going to learn the least do. And we could talk a long time about why that might be. But still, even the kids that the teacher said were low achieving did well. And also the kids that were high achieving. We also have rich and poor kids represented there. Okay, so that's what I want to share with you about dynamic representations. We're using this shared display to create a new level of attention to the distinctions about rate, about motion, about distance, rate, and time. And then we're using the dynamic representations to connect these different concepts. And hopefully that brings to life for you a little bit about what I think those learning science principles mean and what they are. And so now I want to switch examples and talk a little about the collaborative stuff that we've done. And at the end we'll talk a little about the teacher things that we're doing. So this is work I've done with a colleague in Singapore, Chi-Kit Louie, and it's a project called Group Scribbles. It actually builds on a practice that I saw everyone doing here of writing things on Post-it notes and sharing them. But in real classrooms, we've found that it can be very messy very quickly to have kids walking up and posting things. You have things them falling off the walls. And so we had an opportunity in Singapore to give kids tablet computers, and they could have virtual stickies, and here's what that looked like. So every kid had a screen with a virtual pad of sticky notes, and they could write or draw anything they wanted on their sticky note. And there was a private area below and a public shared area above, and by dragging this sticky note up there where it says public, it's going to be posted so everyone can see it. And you know what? If you didn't like it posted, you made a mistake, you just drag it right back down. So this is a way to very quickly get kids posting and sharing and collaborating around ideas. And we particularly didn't want them to have to do a lot of writing in long English sentences to share, which is what many blogging and posting type tools do. They're very texty. We wanted to capture kids' sketches and one or two words, key words, that might signify a concept. And so, we don't have to go through all that. We're in Singapore. They have to teach the kids Chinese because English is the main language in Singapore. And here's a wonderful Chinese example of one of the things they did with Group Scribbles. In the center, I don't speak Chinese, but in the center, there's a key phrase, and each of these diagonals is a specific aspect that you're supposed to learn about. Maybe one is pronunciation, maybe one is metaphors. And the activity was for the kids to brainstorm everything they could know about this Chinese phrase in the middle.
What's the color represent?
Colors can be random, or it's up to the teacher what they mean. So Group Scribbles is a very social convention-oriented system where we give some very simple tools and we let teachers and the kids decide what they want to use them for. And so it can mean everything or nothing. Sometimes it just means it's mine and my color is different from yours. But sometimes we might want to ask them to color code their notes. And you don't have to tell the computer anything that you're doing that. You just agree as a class, for today yellow is going to mean this.
What was the bottom left of this connotations?
Oh, kids do this all the time. This is, I think, personalization in part. Kids post cute little things, and they make little marks on there so they can see theirs up there, where they develop little icons, and so it's like a chop on Chinese art. And so I think that's part of wanting to have a presence in this public space. You see it very, very commonly that.
There's sort of a category that fits, because
yeah, right, maybe right. It could have something to do with the category too. So here's an example in science. We had kids. They were talking about young kids. You can see they're very young. What's going to happen with your heart when you exercise, and will your heart be faster or slower? I think it was what your resting pulse is going to be a minute later, will it be slower or faster? And kids were brainstorming. This is a simple brainstorm. But if you go into a Singapore classroom or conventional work, kids don't talk at all. They're very polite, and very quiet, and very passive. And this tool was good. Look how much was getting up there in just a few minutes of brainstorming with this kind of tool that you could get up on the board. And of course, then the teacher knows a lot more as they read these of what kids are thinking. So that's the formative assessment. So we're both getting kids sharing and collaborating more. And in a version of this that I don't have time to show you, each group at a table can have 3 levels of spaces. I showed you private, going to public, that you can have private going group, and then you can promote things from group to the classroom level. And so that's a great way to do small group stuff, where you first brainstorm as a group of 3 and get everything into your group space, and then you can pick ideas from your group space that you're going to share with the whole class. And the tool enables that.
Can you do it so that they are posting anonymously?
Yes.
Yeah.
In fact.
Some would maybe not want to post unless they.
Right. So the way, by default, everything is anonymous, which is a great feature of the technology. But the teacher can always find out and turn on the easy either on their private laptop or display. That can be important for some kids who seem very disruptive and you want to talk to the kid. So the system actually knows it's not truly anonymous, but one of the big ideas here in collaboration, I think, is to pay attention to the ideas, not who said them. Right? So we want to improve the ideas, we want to focus on the ideas. We don't want to make a big deal out of whatever kids try to wrong. Why is this idea better than that idea? Who wants to speak to this idea? And you'll find kids that don't have the idea, which is become advocates for it. And sometimes the kid who's best putting it up there first isn't the best at expressing it. So the anonymity is a really cool feature. This is an example in math, and this is an exercise you can do where you grid these notes, and you can ask kids to think of different representations for different numbers. And you can see just how creative kids can be about ways to represent fractions. Often much more creative than their teachers would be. And expressing both things that might be problematic and good, because you can have a great conversation about some of the challenges and problems of these representations. What I love that I think was very innovative, it came up with this, see that spiral one for 5/4? A big problem you get into with 5/4 or other things that are bigger than 1 is how do you show you've got more than a unit? And if you do pies, you have to have a second pi, and then you get all confused about what you're counting. But the spiral is the number of times you've gone around. So now 5/4 starts to make some sense as different from 1/4, because 1/4 is just useful distance. You go all the way around, and you've got some more. I thought that was really cool. The kid came up with a spiral. I had never thought of a spiral. So that's group Scribbles. And I was gonna I think we're gonna do this in our workshop though, I want us to try using some of these techniques together as groups, because we're gonna do some small group work together. And let's see. I think it would probably be, we want to end at 1. What time do we want to end? Should we just, around 1. Okay, so we won't actually do this now, but I think I got a sense from attending the group this morning that you're familiar with Think, Pair, Share, and this can be a version of that. That's off by an hour? Yeah, that's fine. Okay, so what are the principles in group Scribbles? We've got some funny numbering on there. We were talking about this in some of the small groups this morning. The collaboration part, one thing it does is it leverages the cognitive diversity of kids in the group. Different kids think differently about the same problem. And getting that diversity out there can help each other have a more robust, more connected, more linked concept than when one of us explains it only our way to everyone. Cognitive diversity, it really encourages kids to elaborate and explain to each other. And I think that's, again, it's really critical. If you just post stuff, and that's the end, you haven't gotten anywhere. It's when you start to look at what was posted and try to discuss or explain or argue about differences, which representation captures what, in what circumstance would you prefer the spiral, and in what circumstance would it not be a good idea. Those are the kind of things where the real deep learning happens. And then really, we wanted to get at supporting kids to express themselves, express their understanding in multiple modalities. And so when you look at that, just look at all the different ways. Someone's got a flower up there, and that was the way he or she wanted to show the different petals. And some kids do things that are much more cut and dry, but we want to enable that expressivity. You see that in the storytelling part in SimCalc too. A key thing is getting kids more comfortable with expressing mathematical ideas. And if they can do that first in a story, or in a gesture, or an emotion, that's great. We don't want to force everyone to have to express things only in very abstract symbols. We want to get that expressivity flowing, and we can move it. Once you got a lot of expression and a lot of ideas on the table, you can start to funnel that towards more formal, more consolidated understandings. But first, let's get it out there. And then it also has the formative assessment principles. It encourages teachers to find out what kids know by getting them to brainstorm, put ideas out there. We emphasize, this is what I was just saying before, not just the initial idea, but what can we do to improve upon ideas. So what could we do to make one of those pictures better? We have a huge set of things about heart rates. Which are the key ones that we might want to focus on if we were going to write a newspaper article about exercise and your heart rate? And so we really want to focus, and that's part of knowledge building, idea improvement, and of course we want teachers to adapt to what kids do. So we want to make learning more adaptive, not just a canned thing. That's what Group Scribbles does. Okay, I'm going to show you one final thing, and I need to switch the, where's Lynn? Now's a good time to switch. I'm going to show you one final thing we're doing with technology. We're working with pre-service teachers in training, on the Cal State campuses, which train a lot of teachers in California. And we really wanted to get to this big idea that I shared with you about the big idea about focusing on student thinking, really centering all the work we do about student thinking. And so we built this tool called a Dynabook, which is started as a digital book, but it's evolved. And I want to show you a little bit of it as a resource in a way that we're starting to build tools to support this practice of centering on student thinking. It's also in the area of proportionality. And yeah, we're up there. And I also, as I showed it to you, we had a great conversation at the lunch table today about reading a book be a social experience. And there's a discussion now, reading books are good, that's individual. And as this design has emerged, this thing that we started out on the book, it's turning out to be less and less of that individual experience. And so let me give you a little bit of a flavor of how that goes. So the Dynabook, remember, is for teachers, not for kids. And so it's organized a little bit differently. You can go to any of these topics like ratio, and you can look at it in different ways. You can participate in an interactive lesson online. You can look at some challenging problems, test your own understanding, or the one I'm going to focus on is video cases. Here's your internet connection. Yes, very good. Okay, so what we have here is we have kids who are solving ratio problems. And this is problem A, problem B, problem C. To make Italian dressing, you need 40 parts vinegar to 90 parts olive oil. How much olive oil do you need to make 65 ounces? Well, it can be an interesting problem to look at, but it's much more interesting if you look at an actual kid. And so what the Dynabook features is kids trying to solve these problems in just 1 to 2 minutes. So let's look a little bit at that.
To make Italian dressing, you need 40 parts of vinegar for 90 parts olive oil. How much olive oil do you need to make 65 ounces of Italian dressing?
So this is more of a proportion following 40 vinegar to 90 olive oil. I need 65 ounces, and I'm finding out how much olive oil. So 40 over 90 equals 65 over whatever the olive oil will be. So this will be a really big number. 90 times 65, which equals 5,850.
Okay, I'm just going to stop there rather than watching the whole thing. One thing that happens with this is she does what kids do, and actually what teachers do in math class. You got some numbers, let's plug and chug. Let's do something with it. And she gets into 5,000s and she's lost. 5,000 what? What is this number I've got? Why am I doing this? And teachers who watch this develop tremendous empathy for Kayla. And what we find is, they want to understand how to get this. And they can watch several of these videos. And now instead of us pushing, here's great pedagogy you ought to do, here's an interactive tool you ought to use, they're hungry for it. How can I help this kid? They want the resources. They're then the rest of the Dynabook can start to show some of those. Now, as it turns out, one of the other things we do, you can do with this, oops, wrong computer, is you can ask the teachers to solve the problem themselves. This has a transcript in it. It's another nice feature because we can get teachers to highlight the parts of the transcript where a particular misconception is. So every video has a transcript, there's a highlighting tool, our highlights can be shared. And then there can be responses. Let's respond to the video. And in the response area, we could ask teachers to do different things. Where do you think the misconception is? How would you help the student? Or we could just ask them to solve the problem. Roschelle and I were in a classroom that was doing this, a classroom of teachers. It was a teacher workshop. And we asked teachers to solve this problem. And we asked them to solve it more than one way. And guess what happened? None of the teachers could solve this problem more than one way. And lots of them did the plug and chug. Right? But when we aggregated all the answers that they did, not all of them were the numeric way. Some of them drew pictures. And some of them actually drew stuff and took a picture with their camera and uploaded what they drew. Some of them did very informal sketches. And when they looked at each other's work, which this tool enabled, because there's this copy to whiteboard feature, which puts everything that you've done on the teacher's whiteboard, they were amazed. If you represent this olive oil and vinegar problem the right way, you don't have to calculate numbers in 5,000. You can solve this by inspection. You can just look at it and see the right answer if you're drawing the right picture. And the teachers had a big insight from that. That this business of telling kids every time you see numbers, find the right formula and put them in, can result in some really difficult, really unnecessary calculation, where some thought ahead about how to conceptually represent the problem can be really fruitful. They can understand the math better, and they don't get lost with calculating the 5,000s. In fact, with olive oil and vinegar, if you realize the big trouble, the difficult part about this problem is you have to realize that you need to form the whole. So if you have the 40 parts and the 90 parts, how many parts do you have all together? We have 130 parts. Now you need to make 65. It's half. Bingo. You know how much you need half of each quantity. Right? So if you draw, teachers get to that by drawing pictures. If you draw a picture of what's going on with parts and wholes and the whole thing, you can get to a much more elegant solution to this kind of problem. Okay, so that's what we're trying to do. And now I'm just going to wrap up with the Dynabook. So I've tried to give you sort of a perspective on different things going on throughout our work. I'm just going to wrap up basically by looking at this slide one last time, reminding us of what we've looked at. So why do we want to use technology? Well, one of the reasons is getting the right display is often really critical to creating the shared focus on the meaningful problem we want to solve. And technology, whether it's plexiglass or computers, sometimes can create a better display. And I'm sure many of you are in that business of creating great displays, but you have to think about the parts to the right. Not only how do we show something beautifully, what's the rich task? Now that we see it, what are we going to do to process it meaningful? We looked at the linked dynamic representations with SimCalc. That's because for learning to happen meaningfully, we need to connect things. And our goal was conceptual understanding. We looked at some of the instant expressive sharing with group Scribbles. What are we doing in terms of learning? Well, we're helping kids learn collaboratively. And what's the key to that? What's the best practice? It's getting the kids to explain, to argue, to conjecture, to predict, all those kind of inquiry words. We also looked with group Scribbles, and there's many other tools for instant feedback, which can do formative assessment. One thing we at SRI, we do lots of research on this. Very common thing is you can get the feedback, and maybe even get the data, but the adapting to what you see is the tricky part. So how do we help teachers adapt to their kids? And it's often very hard. And then I was showing you some of the things we're trying to do with new media to really take to heart this idea that the best teacher professional development is teacher professional development that centers on how students think. And so that's some things I think you should all know and work with as you go forward to build on the great things you're doing and incorporate maybe some of the things that we're learning in the learning sciences. Thanks. And we can take some questions? The Dynabook thing thing is, I've heard something, it will be available. We're still, there's a lot of kinks we're working out. There's a lot I can show you with Dynabook that it does, and there's a lot of kinks still. But I think the concept is exciting. This book of student thinking with resources that teachers can use now that they want to figure out how to help these kids, who are just like kids, they're going to face thoughts. Yeah.
So what would be the audience that you were seeing for Dynabook? Would you really say it sort of encapsulated to one school district, so those teachers could all collaborate? Or would it be nationwide, everybody adds to whiteboards?
So the question Kirsten is asking is, who's the audience for Dynabook? We started out with the Cal State system and the work they do with developing new teachers. Actually, our thought was this should be easier with pre-service because they should be part of the digital natives. And we found it's not really quite true. There's a lot of discomfort among these to-be teachers with technology. And so one of the really striking things when we've done this in the pre-service setting is teachers just say, wow, I've never seen technology used in an intelligent way in teaching before. I just had no idea that you could do this. So yeah, it's been an interesting experience. I think our vision initially, again, because we don't think things are teacher-proof easily, and really getting the activity right, is that this would be something with a leader. But it could be an in-service or a pre-service professional development tool. It could be something where the teachers do some work at home to read, to look at videos, and they come in and do some activities together. And the activity we've been focusing more and more on as the outcome activity of their work is for them to write out an actual script of how they think they would help Kayla. Sentence by sentence. She would say this, and I would say this. And then we can look at those scripts and think about how to improve them. We're trying to get out of lesson plan mode. It's too easy to make lesson plans and not really focus on kids' thinking. And we're finding this exercise of just writing out a script is a nice way to get teachers to think more deeply of how they're going to use these different principles in real teaching.
I have a two-part question.
Yeah.
One, how do we get access to these technologies
Yeah.
that we're creating? And two, if these things are still in progress, do you have any assessment that you do of existing technologies that would help us to know which ones to invest our time into? Because I think there's some good ones out there.
Yeah. Right. These are all in different states of availability. The SimCalc stuff you can download for free from the University of Massachusetts. So if you just that phrase SimCalc, just write SimCalc download, you'll get a copy of that software. And the curricular workbooks that we've used in 7th grade and 8th grade are available for free from SRI. Our website's math.sri.com. It's the website. There are many other tools that do dynamic representations, both in science and in math. I'm a big fan of Geometry Sketchpad and of Fathom, those are for geometry and data analysis, respectively. So there's tools of this class that focus on visualizing and on multiple representations. There's the PET simulations at University of Colorado in science that many people really like. So there's a lot of resources in the first area of dynamic representations. Group Scribbles, you can play with via a server. There's an online server that will let you play with it. If you really want to use it in school, you probably just have to get a license, which we provide for free, and you'd be a little tech support to install it. And it works. The reason why we haven't done that much with Group Scribbles is because it really works best if you have a stylus. And most kids don't have computers with a stylus. Your finger on an iPad or trying to move the mouse to draw things is just too much of a hassle for kids. So it turns out in Singapore, the kids have tablet PCs because of writing Chinese. And so it made sense to test it there. And Dynabook is a work in progress, but email me if you're interested. And when we have a public version, I'll let you know. Actually, all of these things, my email address must be in the program somewhere. And so you can email me questions. And I'll share stuff with you, including the slides, which somehow will get to people. Yeah?
What's the impact of using such tools on the rate covering the curriculum? Maybe the teacher would say, yes, this is is very cool, but they have a large curriculum and they're gonna cover.
Right.
So, did you look into that, or what's the impact of?
Yeah, I know. It's a terrific question. The question is, like, if you do these tools and you go deep into concepts, what about coverage? And we had to confront that very much in scaling upward. Teachers just wouldn't do it if we messed with coverage. And so I'll just tell you the philosophy that I've come to. And it's a philosophy about scale and adoption. And when you deal with scale and adoption, you have to deal with coverage. There's so much pressure around coverage. If you fail to address that question, teachers will ask, you won't get anyone to do what you're doing. And so what I've come to say about it is we need cornerstones. Well, what's a cornerstone? There's 3 or 4 big ideas per year in math. I don't know how many there are in science, but there's big ideas. And so you don't need to use technology for every little thing you're going to do. But let's find those big ideas, big conceptual struggles, where going deep and having a really powerful experience could then be leveraged. And so the philosophy that we've developed at SRI is that most of math teaching is very flat, problem after problem after problem, page after page. And we want to create some peak experiences, and we don't need that many per year usually. And that helps solve the coverage problem. It also helps with the teacher professional development problem because you're focusing on doing the more exciting, more challenging stuff with less material. And then you go deep into the student thinking and everything else because it's only 3 or 4 days per year. We've also talked with some science educators about maybe Science Wednesdays. Again, some schools do special things with science or STEM on Wednesdays. So there's ways you have to think about that question about where do you fit it in to avoid disrupting everything. The rest won't be that.
I assume this applies to adult learning as well.
The question is, does it apply to adult learning? Actually, one of my fondest things with all of this is when adults say, I want to go back and learn science. I want to go back to school now. I want to learn this way. So I think absolutely that these are great ways to work with adults. Many of them have the added burden. They've been through it once, twice, or 3 times already in the standard way. It didn't work for them. And so unless we do something new, it's a non-starter because they already have that experience of failure. So that's a little different than kids. And so it may be more important with adults to break up the experience and do something very different, very engaging to get started. Yeah?
I don't know if anyone's doing anything similar to Dynabook in science.
So we have worked to develop Dynabook with an organization called CAST. You know CAST. CAST is in the Boston area. They come out of the special ed world. And increasingly, I think the special ed world has a lot to teach all of us in the more general education population because they focus on individual kids. Anyway, CAST, before we built this one, they built 2 books for science. I think they're not far along in some adventuresome ways that we are, but they're there as an example. And I can connect you up to the people who have done those. They use some inquiry-based science curriculum to do that. And so, that's sort of the goal, is to do it in science as well. I think they have a really cool project to build this kind of thing as a more open archive, where you've got the structure right, like a wiki kind of thing, but people are putting in examples of kids struggling with problems. And honestly, the way we got a lot of these videos is we just rounded up kids that we either know or our own kids and asked them to solve these problems. It didn't take long, it wasn't hard. It's a really compelling kid video. As we know as educators, we know what kids struggle with. So we know the kind of problems put in front of them. That more likely than not, we're going to get some really interesting thinking to contend with given that problem. Yeah, I think it's a great project. Anything else? I know it's been hot in here, and I thank you for your attention after lunch in a hot room. And I look forward to talking to you.